Hello, uh, this is the live session for Structure, Form and Architecture, the Synergy. It's an NPTEL course. The course instructor is Professor Shubhajit Sadhukan, Assistant Professor at IIT Roorkee. And I am Shreya Shukla. I am the course TA for this semester. I am a PhD scholar at IIT Roorkee. Today we will be doing the assignment 6 for week 6. And I would like to mention it that in these live sessions we do the assignments of previous years. We do not do the assignments of this year, we do the assignments of previous year. We will wait for 5 minutes for everyone to join and then we will start the session. So it has been 5 minutes. No one has joined again yet. So we will see if they join in the between. We will start with the session. So again, hello to everyone. This is the live session for Structure, Form and Architecture, the Synergy. It's an NPTEL course being done by Professor Shobhijit Sadhukan, and I'm the course TA and I'm taking this live session. Today we will be doing assignment 6 of week 6. So these are the 4 terms that have been yeah, so I have already discussed these terms in all the other classes. I will not be covering these. So sorry, it's week 6 syllabus. So week 6 syllabus was 5 courses, 5 chapters were again covered, 5 different parts: shell structures, trusses and space frames, folded plate structures, membrane structures, and pneumatic structures. In shell structures, the format that was followed and the topics that were covered under shell structures were introduction about shell structures, what are shell structures, the loads that happen on shell structures, examples from around the world, Indian examples from other parts of the world, different materials that are used to make shell structures, different typologies of shell structures, for example monoclastic, anticlastic, synclastic types, and then different shapes of shell structures like hyperbole, paraboloid, and other things. And then 2 terms were discussed that define the different shapes or different curvature of shell structures, which is surface of translation and surface of resolution. Advantages and disadvantages were discussed. Then moving on to the 27th lecture, trusses and space frames. Again, a very similar format was followed, uh, like all the other chapters or sections or lectures. Introduction was covered, the different kinds of materials that are used in to make trusses was covered, and the different types of trusses were covered: planar trusses, prismatic trusses, roof trusses, bridge trusses, and different type of trusses based on how the members are put together were also covered. For example, king truss, king post truss, queen post truss, Pratt truss, Harvey truss, and others. Examples of different kinds of trusses were covered from around the world, famous buildings, famous structures that have been constructed throughout the world. Those examples were covered. Disadvantages, advantages of trusses, disadvantages of trusses, and then application of trusses. All these points were covered. Similar was for space frame. Again, space frame is a 3D lattice of trusses. So it's very similar to trusses, so they were both clubbed into the same lecture. Then again, similar topics for space frame was covered, the materials that are being used, different examples from around the world, different shapes being used, and other parts. Then we have folded plate structure. So in folded plate structure, it was covered the introduction, what is a folded plate structure, and then different kind of geometries were shown, how folded plate structures work, and how forces act on folded plate structures, then different types of folded plate structures, the structural behavior of folded plate structures, different materials that are used to make folded plate structures, and then typologies, the applications, examples from around the world again, and then some advantages, disadvantages, etc. Then moving forward to membrane structure. Membrane structure again, what is a membrane structure, how it is defined, how it happens, and what are the components of membrane structures, what are the typologies of membrane structures, what are the materials that are used for membrane structures. Compared to other kind of structures, membrane structures have more technological developed materials, polyesters, ETFE foils, which are not used in other kinds of structures. Usually all these other kind of structures either use steel, concrete, wood, other things, but membrane structures use very different kind of materials compared to other kind of structures. And then different types of membrane structures, whether it is mast supported, frame supported, arch supported, and other things. Then typologies, and then examples from around the world, and different shapes of membrane structures: hyper, conic, barrel vault, and other points were covered. Then again, disadvantages and advantages were covered. Lastly, pneumatic structure, the last lecture of this week, Again, what are pneumatic structures? They're basically structures which use air pressure to stay still. And then different types of pneumatic structures, what are their characteristics, what are the components of pneumatic structures. And pneumatic structure again is very different compared to other kinds of structures that we study, because they have very different kinds of materials and different technology, how it is made, and then different type of pneumatic structures. There are two major types, air inflated and air supported, and then both of those types were discussed in detail, and then examples from around the world were given, and then advantages and disadvantages of both of these kind of types, and then the applications for these structures were given. So this was covered in week 6, and today we will be doing the assignments for week 6. I would like to clarify again that we do previous year assignments in this live session. We do not do this year's assignment. So I have last year's assignments, 2022 assignments, and some questions from further previous years than that. So I have covered, I think today I will be solving around 18 questions. So moving forward, we will start. So first question from the previous year, the following, they have given this image of this leaf, and they are asking that the following is an example of membrane structure, shell structure, folded plate structure, or pneumatic structure. Excuse me. So the reason that they have given a leaf over here and then asking a question based on structure is that most of the structures that are being constructed or that are have developed over these years, and these complicated structures, their inspirations more or less lies in the nature. For example, the shell structures are kind of inspired from various things that exist in the nature, like the shells, seashells, and these animals, and the plants, how they fold, how the leaf, everything somewhere more or less is somewhat inspired from nature. That's why they have added this image of a leaf, and they're asking what kind of structure is this. So to be able to answer this question, we will first try to understand what all the types, 4 options that have been given. So the 4 options that have been given are membrane structure, shell structure, folded plate structure, and pneumatic structure. So I will explain all these 4 terms, and we will answer this question. So membrane structure. So what is a membrane structure? It is basically a structure with a thin flexible surface, which is called a membrane, that carries loads primarily through tension stresses. And it is a structure that is characterized by tensioning of the membrane system, typically with a wire or a cable, to provide the critical structural support to the structure. As per structural and architectural point of view, membrane structures are light and free-form structures, and they span a long distance with the minimum materials used in the manufacturing. They are used to construct roofs, facades, freestanding buildings, building envelopes, skylights, indoor ceilings, or accent closures. So basically, membrane structures use tension in their structure format, where cables and wires are used to create tension in this kind of structure. And that's why, and there is usually a surface that is used in these kind of structures, which are usually fabric surfaces. Shell structure. Shell is basically a type of building enclosure. Shells actually belong to the family of arches. They can be defined as curved or angled structures capable of transmitting loads in more than 2 directions to support. Shells are basically thin, they're curved, they are plate-like structures shaped to transmit applied forces by compressive, tensile, and shear stresses, and that act on the plane of the surface. They are usually constructed of concrete, reinforced with steel mesh, because it's a very thin cell, so usually it's a reinforced concrete that is used to make these kind of shells. And it can function both as a structure, and it can also function just as a covering. And to give some examples, very regular examples, a shell with one curved surface is known as a vault. Basically, vault is like a semi-cylinder. So it has just one curvature, so it's a shell with a single curve, and a shell with double curvature is known as a dome. Matlab, a dome can be seen as a shell with a double curvature because it has two kinds of curves in two directions. And there are more complex forms of shells which are being made now, which the shapes include hyperbolic paraboloids, saddle shapes, the intersecting parabolic volts, and others. We will see some examples further in the presentation. Then pneumatic structures. Pneumatic structure is a type of membrane structure and it is stabilized by the pressure of compressed air. Pneumatic structures are characterized by slightly higher pressure of internal air above the outside pressures. So the concept of pneumatic structure is that how this kind of structure works is basically that the air pressure inside this structure is higher compared to the air pressure that is outside the structure. That's how this kind of structure stands still. And these structures are supported by pressurized air within the inflated building elements that are shaped to carry the loads in a traditional manner. The roof membrane of the pneumatic structure is made from rubber or reinforced films using industrial fabrics coated with polymers. One of the most famous material that is used for pneumatic structures are ETFE foils. Folded plate structure. Folded plate structures are assemblies of flat plates or slabs inclined in different directions. So basically these are plain flats but they're joined together at some angles or different directions along their longitudinal edges. In this way, the structural system is capable of carrying loads without the need for additional supporting beams along mutual edges. This technique originated in Germany in the 1920s and it became popular to construct roofs for industrial warehouses and public buildings. Modern folded plate structures are typically made of cast in situ or precast reinforced concrete or steel plate. So these modern plate structures it originated in Germany as a part to create roofs, but nowadays folded plate structures are actually used in any form. They're used as walls also, they're used as floors also, and they're usually either made cast in situ or they're precast or they're made of steel plate. So there are various materials usually which are used for folded plate structures, but most common is the RCC. So as you can see, this going back to this image, we have seen how all these four kinds of structures look like. So going back to this image, you can clearly see that the pattern in the leaf is like a zigzag pattern, which is called a chevron pattern also. So this chevron pattern is a characteristic of a folded plate structure. So our answer would be folded plate structure. Moving on to the next question. The following illustration is an example of dash curvature: monoclastic, synclastic, anticlastic, and bipolar. So we have to understand all these terms to be able to, all these types of curvatures to be able to answer this question. So I would explain these terms and then we will be able to answer these questions. Monoclastic, a single curvature shell is monoclastic. So basically all these three things, monoclastic, synclastic and anticlastic, there are types of curvatures and they're defined by how one curve is acting around either an axis or around a curve. So in monoclastic what happens is that a single curvature is there. So there's just one curvature, there are not two curves, there's just one curvature and it is curved in one direction and it comes in the form of barrel bolts or conoid shells. So the example of a monoclastic structure would be a barrel bolt because it's one curve, a semicircle, which is going in one direction of one axis, which creates a semi-cylindrical form. So that is monoclastic. It is just one curve and it goes around one axis. That curve is going around one axis. That's monoclastic. Synclastic. These shells are doubly curved and have a similar curvature in each direction. Synclastic surfaces are those in which the centers or curvature are on the same side of the surface. And an example of a synclastic is a dome, and because it is doubly curved and it can be formed by rotating a curved line around an axis. So what monoclastic is just one curve which is going around one axis. What happens in synclastic is that it is doubly curved. It has two curves. Anticlastic and synclastic both have double curves. And basically what happens in synclastic is that for example, this is one curve and this is another curve. The center of both of these curves is on the same side. So that's how synclastic is defined. A major example is a dome and also other kinds of shapes. As you can see in the image below, that's also an example of synclastic. Then coming to anticlastic. Anticlastic surfaces are those in which the centers of curvatures are located on opposite sides of the surface. So if you can see the image here, the first image is an anticlastic surface. So this curve that is going, the center of that curve would be in this direction. And then this curve which is going, the center of that curvature would be on the opposite direction. So that's an anticlastic surface. And another way to understand anticlastic surface is that for example, I don't have any kind of shapes, otherwise I would have been able to explain it better. So what is happening in monoclastic is that this is a curve, and then there is an axis and it is going in that direction. So that's forming a monoclastic thing. Then what is happening in synclastic is that this is one curve, this is another, and this is another curve. And this one curve is sliding on this curve, forming that shape. Same is with anticlastic. This is one curve and this is another curve. And the shape that is, then we move this one curve on this curve, and then the shape that generates is anticlastic. So examples of anticlastic are saddle points, conoids, hyperbolic paraboloid, hyperboloids, and they're all considered anticlastic shells because they are saddle shaped with different curvatures in each direction, and straight lines can be drawn off the surface. And yeah. So yeah, what I was telling about the axes and how the curvature is going, you can see the small diagrams that are above. Along with it, you can see how the curve is moving in the direction of the axis or another curve, and how those shapes are being created. So again, our question was that what kind of shape is this? So as what we have learned from right now, it's very evident that the answer is synclastic because it has curvature in two curvatures, so it's not monoclastic, and it has both the curvatures, the center point of both the curvatures is in the same direction, so it's synclastic. And bipolar is not a term related with curvature, so I don't know, I have not mentioned that. Moving forward to the third question. Sky Song at Arizona State University campus is a dash tensile structure: high power, conic, vault, or inflatable. So we will see first how Sky Song at Arizona State University campus looks like, and then we will understand all these four terms, and then we will answer this question. Excuse me. Yeah, so this is how the Sky Song at Arizona State University look like. It's a structure there. It's a mixed-use project. It consists of 1.2 million square feet of office, research and retail space, and a hotel conference center. And basically, it's a whole complex. And then this structure that stands in front of it, is I think it's probably somewhere in the middle of the whole compound. The architects of this were FTL Design Engineering Studio. The entire area of this place is 4,645 meters square, and the manufacturers of this are Fabritech Structures. And now we will understand what all these four terms mean: hyper, conic, volt, and inflatable. So in terms of structures, so conical tension structures, they're highly effective for covering large areas, and it's called conical tension structure because it looks like a cone in its curvature, and it is easily identified by its tent-like shape. It looks like a tent. we all know how a cone looks like, right? And that's the shape of a tent usually. So that's how it is easily identifiable. The conical designs can feature either single or multiple masts. Masts are basically columns or members or posts which are used to attach the tension cables, wires, or the fabrics too. So basically in conical tension structures, there can be one mast, there can be many masts supporting the entire structure. For both our design options, membranes are tensioned between a ring at the pinnacle and the perimeter support columns. Cones are especially effective in areas that need to comply with high rain or snow load regulations. So the reason being that if there is high rain and there is a lot of snow load, so this cone kind of shape works very well is that it will not gather on the roof. For example, if it's a high snowfall area, it will not gather on the roof, it will fall down. So that's why cones or slopes are very important in those kinds of areas which have high rainfall and high snow load. High power on anticlastic structure. It is one of the most common of all the tension membrane structures due to its aesthetically pleasing look. Hyperbolic shapes are notable for their excellence with shape retention and water runoff. These structures rely on two opposing curvatures. Like I have just mentioned, I have just talked about anticlastic structures. There are two opposing curvatures happening in this kind of shape, and it is called anticlastic for their stability. This type of structure is ideal for a shade over seating or high traffic walkways. Parallel arch or barrel vault structure. They're symmetrical curved parallel arch designs from an incredibly functional tension member canopy that can span long distances such as sports arenas or smaller areas such as entryways. Depending on the spans, a barrel vault system can be a cost-effective way to incorporate the tensile member on a project due to the repetitive nature of the design and efficiencies of mates. Again, parallel arch or barrel vault structure is the same thing, that there is an arch which is moving in this one axis direction and it's creating a space structure. It is comparatively the simplest looking kind of tension structures, membrane structures that we are talking about here. And it's also, it can be cost effective because it is easier to incorporate the tensile member on a project due to the repetitive nature of the design, because it's just one curve that's happening. Inflatable structures. Most commonly they are used in biodomes and for users to set up a temporary exhibition hall using pneumatic air inflating methods. So inflatable structures are basically pneumatic structures. These all are examples of membrane structures, and these inflatable structures are mostly used for biodomes. We have a very famous example from that. I'm forgetting the name of the place. It's in UK, but I'm forgetting the name of the place. We'll see that later. For users to set up a temporary exhibition hall using pneumatic air flaking method. So, showing the example of all these four structures. So that is high power, which is basically anticlastic. It has two curvatures, one in this direction, one in that direction. Then we have barrel vault, which is basically a vault kind of thing, similar curvature that's happening everywhere. Conic, it looks like a cone, it is very easily identifiable. Then inflatable, it's like a dome, it is using pneumatic air to stand up. And yeah, so moving back to a question. The question was that Sky Song at Arizona State University campus is a dash tensile structure. Which of the following? So as you can see very clearly that it's not volt, it's not inflatable, and hyper and conic we come with, but it is very evident that it is conic because it looks like a cone. Although this has a curvature and different angles, but this is not hyper because hyper does not have a cone looking structure, and this has various cone looking structures. So this is definitely a conic tensile structure. So the answer would be conic. Next question number 4. The Millennium Dome in London is an appropriate example of dash structure. Membrane structure, folded plate structure, pneumatic structure, or a diode structure. So we will see how Millennium Dome looks like first, and then we will see, because some of these terms I have already covered, but I have still added the information later in this PPT, so I will quickly cover all those points. So we will move forward. So this is how the Millennium Dome looks like. It's a large dome-shaped building on the Greenwich Peninsula in southeast London, England, and it houses a major exhibition celebrating the beginning of the third millennium. Currently, as of 2022, it is the ninth largest building in the world by usable volume, and it opened in 1999 to celebrate the third millennia. Uh, the height of the entire dome is 95 meters. The architectural style is here used in this dome is high-tech architecture. The owners of this building are Anshud's Entertainment Group. The architectural firm was RSHP. The architects were Richard Rogers and Mike Davies, and the engineer was Ian Liddell. So this is how the Millennium Dome looks like, and you can see how there are various masts going up and how those cables are tensioned and they're holding the surface of the dome together. So moving forward, membrane, folded plate, pneumatic and diagram. These were the four terms that we had to see. So membrane structures, as we have discussed, just some points, just a few questions ago. They're thin, flexible surfaces that carry load primarily through tensile stresses, and it is a structure that is characterized by the tensioning of the member systems to provide the critical structural support to the structure. And they're light, they're free form structures used for long spans. So these are some of the features of membrane structures. Then folded plate structures. Folded plate structures are flat plates which are joined together at different angles, and that's how they carry load, and without the need of additional supporting beams they can carry more load because of this technique. It is used in a lot of ways now. It is used as a roof, it is used as a wall, anything. It can just be used as a canopy also. Then pneumatic structures are a type of membrane structures which are stabilized by compressed air and a high pressure air. The air pressure inside the structure is always higher compared to the outside. That's how the structure stays afloat. Then diagrid, because diagrid we have covered in the last week lecture, but I will again mention what is a diagrid structure. So a diagrid structure is a framework of diagonally intersecting metal, concrete or wooden beams that are used in the construction of buildings and roofs. It is basically and diagonal, it's like a grid but not orthogonally. It's a grid that is diagonally formed. It requires less structural steel compared to a conventional steel frame. One of the most famous example is Hearst Tower in NYC, and it was designed by Norman Foster. Norman Foster is actually known for all the kinds of diagrid structures that he has made, and the Hearst Tower used 21% less steel than a standard design. That's how much steel you can save by using a diagrid structure rather than a conventional steel structure to support your building. And the diagrid obviates the need of columns and can be used to make large column-free expanses of roofing. So these are the four terms that were mentioned. And going back, when you look at this image carefully, you can see that it has masts, it has cables which are supporting a membrane. So it's definitely not diagrid structure, it's definitely not a folded plate structure, and it could have, and if you see, because pneumatic structures also have a similar shape as membrane structures, because it is a membrane structure itself. You can see very clearly that this is a membrane structure specifically, not a pneumatic structure, because it is being supported by tensioned cables and masts. So our answer would be membrane. Now next, question number 5. The following illustration is of what? They have mentioned 4 kinds of trusses and they have given one image, and now they're asking that you have to Yeah, so Warren Truss, Baltimore Truss, Bowstring Truss, and Harvey Truss. So we will learn all how these four trusses look like and what these four trusses do, and then we will answer this question. And to be able to understand two of these trusses, we should know what a Pratt truss is, otherwise we won't be able to understand the other two trusses that come here. So I've also mentioned what a Pratt truss is. So in a Pratt truss, the vertical members are in compression and the diagonal members are in tension. And it simplifies and produces a more efficient design since the steel in the diagonal members can be reduced. So if we go by the shape, you can see in the bottom right corner Pratt truss how it looks like. So there, these are truss ends, and then there's a triangle forming at the ends. That is the diagonal that is being used. That's how the Pratt truss looks like. Warren truss. Warren truss is another very popular truss structure system, and it is easily identified by its construction from equilateral triangles. One of the main advantages of a Warren truss is its ability to spread the load evenly across a number of members. So this is how a Warren truss looks like. If you see the first image, they are basically triangles put together. It's very easy to understand because it's the most easier planar looking truss, just triangles put together. That's how Warren truss looks like. Baltimore truss. Baltimore truss is a subclass of the Pratt truss. So I just showed you what a Pratt truss looks like. Okay, so there is one vertical member and one diagonal member. Vertical members are usually in compression and the diagonal members are in tension in Pratt trusses. So Baltimore truss is a subclass of Pratt truss, and a Baltimore truss has additional bracing in the lower section of the truss to prevent buckling in the compression members and to control deflection. It is mainly used for rail bridges and showing off a simple and very strong design. So you can see the Baltimore truss in the left side bottom corner. So as you can see, if you compare Baltimore truss and Pratt truss, they both look same. The only difference, it's a subtype of Pratt truss, and how it is different from Pratt truss is that it has more bracing compared to Pratt truss. In the bottom part of the truss, they have more triangles forming, they have more smaller struts supporting the larger tension members, tension struts or tension drafters or tension components, so that these components don't buckle. So because if as it has been mentioned that it is mainly being used in railway bridges, so for that we need longer spans, and if a longer span is happening, then the chances of buckling is also increasing. So to prevent that kind of buckling, we support the side strut with again a smaller strut, and that's how Baltimore truss forms, and that's how it looks like. And basically more braces or more sections of steel or whatever you can say are added over here. Then bowstring truss. A bowstring truss is a structural device commonly used in bridge building, again, and it is less often in industrial architecture. It is used to span wide column-free spaces. It consists of an arched beam, the bow, joined at each end by a straight beam, the string. And with diagonal support beams joining the two. So what is happening in bowstring is that there's an arch. It's called bowstring because it has bows and strings. There's an arch. Uh, there's an arched beam joined at each end by a straight beam, which is called the string. So it's an arched beam, and all these beams are joined at each end. The arched beam along with the base beam, that joined by straight beams, which are called strings. And then to give more support, diagonal beams are also added. So if you can see in the right top corner, this is how a bowstring truss looks like. There's an arched beam, it's called a bow, and there's a base beam, and the arch beam and the base beam are being joined by different strings, which are the vertical beams, and then the entire structure is being made more stable by adding diagonal beams. So this is how a bowstring truss looks like. Now coming to Harvey truss. So Harvey trusses are essentially the opposite of Pratt trusses in terms of geometry. In fact, looking at a Pratt truss upside down will visualize a Harvey truss. The entire structure is still relatively same, but the diagonal braces are now occupying the opposite or unoccupied joints. The switch in position of the diagonal members has a very important effect structurally. So you can see that Harvey truss is actually the opposite of Pratt truss. So if you see both of these images together, you can see how they both are literally exactly like mirror images of each other. So that's how Harvey truss looks like. So our question was that the following diagram or the following figure, the illustration that has been given, what kind of a truss is this? So the options were Warren, Baltimore, Bowstring and Harvey. And as we can see very easily from the different images, it is Warren truss. It is the simplest triangular truss there is. So yeah, our answer would be Warren truss. Question number 6. In which of the following building folded plate structure was used? Bihar Museum, Patna, Church of Notre Dame de Royan, France, Yokohama International Port Terminal, Japan, and both B and C. So to be able to answer this question, we would just a second. I'll just. Yeah. So, yeah, we will see first how all these three buildings look like and what are folded plate structures, and then we would answer this question. And just because I cover certain terms and definitions or certain typologies in the start of the session, I still talk about those terminologies again in the next question, because sometimes people join in between and they miss the first part, so they're not aware of the terminologies or not revised with the terminologies. That's why I like doing this, that although I have talked about folded plate structure again before in the session today, in the previous question, the first or second question, I don't remember which one, I would still define what a folded plate structure is and what it looks like, so the people who have joined later can also catch up with the question. So this is how a folded plate structure looks like, and there are also assemblies of flat plates or slabs inclined in different directions and joined along their longitudinal edges. They can be used as roofs, as you can see in the first image. They can be used as walls, as you can see in the next image. And it is capable of carrying loads without the need for additional supporting beams along mutual edges. And this technique originated in Germany in 1920s, and it became popular to construct roofs for industrial warehouses and public buildings. But right now we use it for all forms. We also use folded plate structure in staircases, and are typically made either in cast in situ or from precast reinforced concrete or usually steel plates. Moving forward, we will see how all these three buildings look like. So this is how these three buildings look like. Bihar Museum, Church of Notre Dame de Royan, France, and Yokohama International Port Terminal, Japan. And you can see very evidently, so the question was which of the following buildings folded plate structure has been used. As we can see clearly that in Bihar Museum, Patna, we don't see the folded plate structure anywhere. And while in Church of Notre Dame de Royan, you can see the folded plate being used in the wall surfaces, and in the Yokohama International Port Terminal, you can see folded plate being used in the entire surface of the roof, you can say. So our answer would be both B and C, both Church of Notre Dame de Royan, France, and Yokohama International Port Terminal, Japan. They both have folded plate structures. So to be able to answer these kind of questions, you have to actually remember how certain buildings look like, and these are not these are quite famous buildings, and you have to be aware of how they look like to be able to answer these questions. Otherwise, it would be difficult. So yeah, keep this in point that you remember how the most famous buildings look like. And if you remember how they usually look like and what features do they have, what characteristics they have, and then you can very easily answer these kinds of questions, because if you remember, if you can visualize what the place looks like, what the building or the structure looks like, you can very easily answer any kind of question. Shenzhen Universiade Sports Center in China is an example of arch structure, folded plate structure, pneumatic structure, or dome structure. So again, similar way, I would be covering all these questions. First, I will talk about how the building that has been mentioned, how it looks like. I will also tell you a little about certain kind of features of these kind of buildings so that you can remember these buildings easily. If you remember certain kinds of features or certain facts about some buildings, it's easier to remember other things about them. So that's why I add images and a little information about all of these buildings. And again, then I will mention all these four kinds of options that have been mentioned, and then we will answer this question. So Shenzhen Universiade Sports Center, it is also called Shenzhen Universiade Center, Longgang Universiade Sports Center, or Longgang Stadium. It's a multi-use sports facility complex in Longgang, Shenzhen, Guangdong, China. Then the architecture firm that made this building was Gherkin Marg and Partners. The place opened in August 2011, and it is located in Guangdong province in China. So this is how it looks like. You can see, and then we will move forward with all these four terms. So I would cover arch and dome first, and then I will briefly cover folded plate and pneumatic structures, because I have already discussed those terms, but I still like mentioning those terms again so that people who have joined later can also catch up. But I will not go in detail as much, but I will quickly mention what those things look like. So yeah, so this is how the building looks like. Please remember, and I would also try to add more images next time for the buildings so that we can see it from different angles. Arch structure. Architecture arch is an opening in a structure that is curved on top and designed to distribute weight. So the basic function of an arch, or the basic characteristic of an arch, was that it had a curve on top, and then usually the arches were designed to just distribute weight. But right now arches are used not just for taking load, they are also used just aesthetically or just like a structure. For example, the image that I've added right here, it's just a structure. It has no significance architecturally, in the sense that functionally it has no significance. It's just an arch, it's just a structure. So arches are self-supporting compressive structures. Arches are actually compressive structure. They take all the compressive loads and transfer it, and they are stabilized by the force of gravity acting on their weight, which makes them very stable and efficient and capable of larger spans. And also capable of supporting greater loads than horizontal beams. Sorry. Then a dome. A dome is a rounded roof with a circular base. It's shaped like an arch in all directions. A very easy example of way to understand arch is that there's an arch, and then you rotate the arch around an axis and a dome forms. Firstly, the domes were used in Middle East and North Africa, and then it spread to other parts of the Islamic world. And because of its distinctive form the dome has, it became a symbol of Islamic architecture later. But right now in modern times, we use this dome not just in Islamic architecture or in some kind of churches or other place, but we have actually modernized this kind of technique. We use different kinds of domes. We are using thin shells to make large domes. We are using membrane structures to make domes. Basically, we're just retaining the shape of a dome, which is like a semi-sphere or just tiny curvature. For example, the Millennium Dome that has a very small, the span is usually very high compared to the height, which makes the curve very less. It's not a semi-cylinder, but yeah, that's how dome has evolved over the time. As you can see in the image that I've also added, it's just a structure. It's a dome-like structure, but it's not like just a part of a building. It's itself is the entire building. That's how domes have developed. And they have double curvature. They have curvature in both the sides, and as I have mentioned before, it's a synclastic type of curvature. And because it has double curvature, the resulting structure is much stiffer and it is stronger than a single curved structure. A single curved structure would be a barrel vault. Oh yeah, that's mentioned here, such as a barrel shell. Then pneumatic structures, we have discussed it 2-3 times, so I'm not going to go in detail here. I'll just cover 2 points. That they are a type of membrane structure, and they are stabilized by the pressure of compressed air. That the air inside these kind of structure is at higher pressure compared to the air outside the structure. And they are usually made with quite technologically advanced materials like ETFE foils and not traditional materials. Then folded plate structures are just different plates put together, joined together at longitudinal edges at some kind of angle, and they're capable of carrying a lot of loads. So if you see the 4 points that were mentioned, arch structure, how an arch looks like, we all know. If you all are a part of architecture, if you're studying architecture or design, you know what an arch is. And a dome, what a dome is also looks like. And because of all the lectures that you have seen in the NPTEL course also, and all the live sessions you have taken, we very well know what a pneumatic structure looks like also, and what a folded plate structure also looks like. So we know how all these 4 kinds of things look like. So going back, we look at this building. So it's definitely not an arch, it's not a dome, and it's also not pneumatic, because pneumatic structure is very easily identifiable. It looks like a balloon kind of thing, inflated thing. So it's quite evident that this is folded plate structure. It's a different kind of folded plate structure, as we have seen in the examples that we just see chevron pattern usually in spans. But this is a folded plate structure. Why? Because there is a flat surface which is stuck together at an angle to another surface along its edge. That's why it's a folded plate structure. Although this shape is quite different than what other examples we have seen, but yeah, this is an example of folded plate only, because the plates are joined at an angle, so they're like kind of folded. So yeah. So yeah, the answer would be folded plate structure. Moving forward, question number 8. Which of the following stadium uses membrane structure for its roof? National Stadium of Brasilia, Oldenburg Stadium of Germany, and Munich Olympic Stadium, and all 3 of them. So we will see what how all these 3 structures look like, and we will cover in short what membrane structure is. So I have already mentioned, I will just not go in detail again, but there's flexible surface membranes. They carry load through tensile structures, they use masts and cables for tensioning, and these are some of the examples of membrane structures. And yeah, so we will see how these 3 buildings look like. All these things, all these 3 buildings are stadiums, and we will see how it looks like. So usually this is a covering that has been on the stadiums. It's like a covering for the seatings. So this is National Stadium of Brasilia. You can see the seating here, the ground here, and you can also see the roof kind of structure over here. Now the Oldenburg Stadium as Germany, as you can very clearly see how it looks like. It looks like a cone. It's very similar to Sky Song, we know. if you remember Sky Song from the previous question. This is how Oldenburg Stadium, Germany, the structure looks like at Oldenburg Stadium, Germany. Then Munich Olympic Stadium. This is how the Munich Olympic Stadium looks like from inside. There is a lot of seating, there is this pitch and everything, and then there is the structure that is covering the seating area to give it shade. So if you can see, all three of them kind of look similar in the way that there is a membrane kind of structure covering the seatings very clearly. So our answer would be all three of them, all A, B, C. And excuse me. Yeah, and like I said before, I would again mention it that you have to remember how these places look like. Otherwise, you will not be able to answer these questions. And just because in a question a stadium is mentioned does not mean it will always be a membrane structure. Some of the stadiums can have different kinds of structures also. So do not think that all kind of stadiums only use membrane structures. These stadiums use membrane structures, but some of the stadiums actually use different kinds of structures also. So that's not a thing that all stadiums use this kind of structure only. It's common, but it's not always the case. So you have to remember how these places look like to be able to answer these kind of questions. Then moving to question 9. US Pavilion Expo 70 is an example of coffer slab structure, air supported pneumatic structure, folded plate structure, and inflatable pneumatic structure. So in this case, we have two options that are given here are actually two types of pneumatic structures. So we will cover that, how these two type of pneumatic structures, air supported and inflatable, are different from each other. We will talk about coffer slab structure, and we will very briefly talk about folded plate structure because we have literally covered it in 4 or 5 questions now. And we will also see how the US Pavilion at Expo 17 looks like. So this is how the US Pavilion at Expo 17 looks like. The Expo 70 was done in Osaka, Japan. So the US Pavilion for Expo 70 in Osaka features a roof covering 10,000 square feet with a clear span of 262 by 460 feet. Although I am myself more used to or more familiar with meter, but I got these dimensions in feet only, so I've mentioned it in feet. I would try to mention the dimensions. I will try that I would cover it in meter. Otherwise, things get very confusing if you try to remember dimensions or just to recall anything in both kinds of dimensions, feet and meter. And because meter is the universal metric system, I would try to cover the dimensions in meter. So the clear span was around 262 by 460 feet, and the total weight of the air supported portion is about 1 pound per square foot. The high strength steel cables, up to 450 feet long are arrayed in a diamond grid. So basically steel cables have been used in a diamond grid, just like we saw in tire grid structures. There is no tension ring used in this. In plan, the roof shape follows the equation of a super ellipse, an ellipse with square corners. So it's a super ellipse, an ellipse with a square corner, and this is how it looks externally, the first image, and the image on the right, that's how it looks internally. And you can see two very tiny humans standing there also. So yeah, now moving forward, coffer slab. Coffer slab is a ribbed structure with reinforced ribs in the lower zone which have mutually perpendicular arrangement. It's also called a waffle slab because it looks like a waffle. It's also called a two-way joist slab. It's basically a concrete slab made of reinforced concrete with concrete ribs running in 2 directions on its underside. The name waffle comes from the grid pattern created by the reinforcing ribs. So basically there are ribs which are perpendicular, and they run in both directions, which makes it look like a grid, and it looks like a waffle if you all are familiar, or if you are familiar with what a waffle is, it's a dish which looks like this. Exactly, that's why it's called a waffle slab. And waffle slabs are preferred for spans greater than 40 feet, which is around 12 meter, and they are much stronger than flat slabs, and also flat slab with draw planners, two-way slabs, one-way slabs, and one-way joist slabs. So they are much stronger compared to all these kinds of slabs. The reason being that both the sides are reinforced droppings. This coffer, this reinforced ribs that are running make it very stable. That's why it becomes very, very strong. Now folded plate structure, again different kinds of slabs that are joined at inclined directions along the longitudinal edges. Then air supported pneumatic structure. So in air supported pneumatic structure, they have air higher than the atmospheric pressure supporting the envelope. So the air inside this kind of structure is higher than the atmospheric pressure supporting the envelope or the membrane or the fabric, you can say. Airlocks or revolving doors help to maintain the internal pressure. So the pressure that is maintained inside this kind of structure is with the help of airlocks or revolving doors, and air must be constantly provided. And in this kind of structure, another source is used to provide air constantly to maintain the pressure. The lifespan of these kind of structures is usually 20 to 25 years. They are either anchored to the ground or to a wall that leakage is prevented, leakage of air, because you have to maintain the pressure. So you have to make it leak proof. You have to make sure that there is no leakage happening here. So it is anchored to the ground usually, or it is anchored to a wall so that leakage doesn't happen. They have relative low cost and they can be installed easily. They can be installed very easily in any place, and they have relatively low cost compared to other kind of structures. And then inflatable pneumatic structure. Inflatable pneumatic structure, like a very simple example would be if you have seen those rafting boats. They are inflatable pneumatic structures. Basically, there is a structure that you have filled with air and it inflates. So the supporting frames consist of air under high pressure. So what happens in inflatable pneumatic structure is that you can imagine that two layer of things are going, like it's like a structure which is filled with air. So what was happening in air supported pneumatic structure was that this is the shell of the or the cover or the envelope of the structure, and the air was inside the whole structure. What happens in inflatable pneumatic structure is like that it's like a shape, it's like a shape of a balloon. Consider it like a balloon of a some shape, and then that thing is filled with air, with high pressure air, and that inflates. So internal pressure of the buildings remains at atmospheric pressure. So the inside of the building does not have to be at higher pressure, because the whole thing, the balloon kind of thing, that is or the envelope kind of thing, is filled with the high pressure thing. So the inside of the building is at atmospheric pressure, just like the outside. There is no restriction in number and size of openings also. For example, we had a restriction in opening sizes or numbers in air supported structures because we have to avoid leakage. And they have potential to support an attached structure also. So yeah. So our question was, US Pavilion Expo 70 is an example of coffer slab structure, air supported pneumatic structure, folded plate structure, or inflatable pneumatic structure. So if you look at this image, you can see that it's an inflatable pneumatic structure. 10th question. Baha'i Temple in New Delhi is an example of. So dome structure, diagrid structure, shell structure, or pneumatic structure. So Baha'i Temple is a temple located in New Delhi. I will show, it's very famously known as Lotus Temple, and I will show the image of that later, and I will cover some facts, and then I will cover these terms, and then we will answer this question. So this is what the Lotus Temple looks like. Sorry for a bad image. I could not find a proper good resolution image. So it's a temple located in Delhi, India, is a Baha'i house of worship. Baha'i is a religion, by the way, that was dedicated in December 1989. And notable for its lotus-like shape, it has become a prominent attraction in the city. The building is composed of 27 freestanding marble-clad petals. These are marble-clad petals, and there are 27 freestanding marble-clad petals arranged in clusters of 3 to form 9 sides, with 9 doors opening onto a central hall. So there are 9 openings here, and there are and these all these openings lead to a central hall. So it's a type. The type is a religious type. It's a house of worship, but it does not have any deity or anything inside, and people of all religion are welcome here. The style is expressionist. The height is 32.7 meters. Diameter is 70 meters. The structural system that has been used is concrete frame and precast concrete ribbed roof. The architects are Faribros Sahaba, and the structural engineers were Flint and Niels COWI. Now, shell structure. We have covered what a shell structure is in the previous questions. So it's like a curved plate structure shaped to transmit applied forces on it, and it's angled. It can be in. Can have various curvatures in different shapes and other things. The pneumatic structure, we have just talked about it. It uses the idea of compressed air at high pressure to make the structure stand afloat. Then dome, we just talked about also, that it's basically a double curvature shell, and it results in much stiffer and stronger than a single curved surface. And it is rounded, it has a circular base, it's shaped like an arch in all directions and other things. And we also covered what a diagrid looks like. What a diagrid is, it's a diagonal grid. It's not a orthogonal grid, it's a diagonal grid, and it is a mode of construction to support the buildings to take load, and it is quite good because it helps in creating spaces which can be of longer spans, and it uses a comparatively less amount of steel than the conventional systems. So yeah, these are the 4 types, and we have again revised how all these 4 things look like. So going back here, so this is definitely not a diagrid structure because no diagrid is being used here. It's not a pneumatic structure because it's made of concrete shell, concrete, we know that. And it's not a dome, very evident. Dome has a very distinctive shape and we can easily identify it. And you can see how different kinds of shells are being added together in a shape to create this kind of building. Different kinds of shells joined together to create this kind of building, which makes it an example of shell structure. So our answer would be shell structure. Now question number 11. Which of the following is not a member of a truss? King post, rafter, purlin, or hoop iron? So we will see what all these members mean in a truss, and then we will answer this question. So king post is a central vertical post used in architectural or bridge designs, working in tension to support a beam from a truss apex above. So what a king post is basically, there is a truss, a triangular truss. So the center vertical post, the central post that is used in trusses is called king post. Rafter. A rafter is a long board that supports the peak of a roof. Rafters are a type of beam, a heavy supportive board that holds up whatever is above in a building. So if this is a truss, then this part is called a rafter. If you can see the image in the between, you can see what is a rafter. It's basically a beam that is taking the load of the roof, and it supports the peak of the roof. The peak of the roof is supported by this rafter. Purlin. A purlin is a longitudinal, horizontal, and structural member in a roof. So, purlins are usually perpendicular to rafters. They support the rafters. They are longitudinal. They are longitudinal, and they are uh, the span of the whole roof would be the span of the purlin, and they support the rafter. And if you can see in the diagram what a purlin looks like. Then a hoop iron, it's a multi-use steel strip. Hoop iron is a steel strip that is commonly used for bracing non-structural timber and bonding masonry. So it is used in timber and bonding masonry. It's also used with timber. It's also used with masonry. There were some examples when hoop was being used. Basically, it is used. Iron is put with the timber or the in between the masonry to provide more bracing. So that is hoop iron. So this is another detailed diagram of what a typical king post roof truss looks like and different members, just to understand what it looks like. So below we have the tie beam, then the central strut is what we call a king post. Then these then the triangular parts that join the peak with the base are called rafters, and then the purlins go which support the roof, and these are the most important parts. And then the more joining diagonals are called struts. Then we have wall plates and supporting wall, and the peak of the king post is called ridge board if it is used there. So these are some of the parts, the important parts of a truss. So our question was, which of the following is not a member of a truss? So exactly from going here, we have rafter, we have purlin, and we have king post. So our answer would be hoop iron. Hoop iron is not a part of a truss. Other things are. Eden project. Yeah, Eden project is the one that I was mentioning before, the dome-like structure. In Eden project, in United Kingdom is an example of folded plate structure, pneumatic structure, space frame, or dia-wood structure. So this is how the Eden project in UK looks like. It's basically a biome. The Eden project is a visitor attraction in Cornwall, England, UK. The project is located in a reclaimed China clay pit. The complex is dominated by two huge enclosures consisting of adjoining domes that house thousands of plant species, and each enclosure emulates a natural biome. The biomes consist of hundreds of hexagonal and pentagonal ethylene tetrafluoroethylene (ETFE) inflated cells. This is what ETFE looks like, supported by geodesic tubular steel domes. These are geodesic tubular steel domes, and they have this layer of ethylene tetrafluoroethylene on it, ETFE, and hexagonal and pentagonal shapes are being used in this kind of dome. The architect is Nicholas Grimshaw. The architectural style is high-tech. The construction started in 98 and it opened in 2001, 3 years. The firm was Grimshaw Architects and the service engineer was Arup. So we have seen what a pneumatic structure is. I will not again go in detail here. So it's just a structure that is characterized by higher pressure of internal air above the outside pressure. We know what a folded plate structure is. There are plates that are inclined in different directions and joined together along their longitudinal edges, and they can carry a lot of load. In space frames are basically 3D lattice structures made up from linked pyramids or tetrahedra into a 2-layer or 3-layer triangulated framework. Different tetrahedrons. Tetrahedrons have 4 sides of triangles and a base, square base. That is what a tetrahedron is. Or pyramids, you can say square pyramid or a triangle pyramid. All these tetrahedrons are attached together to form a 3D lattice. That is what a space frame is. It's a 3D truss basically. It's a prismatic truss. No, sorry. It's a 3D form of a prismatic truss. Two-layer or three-layer triangulated framework. So that's, and this is how a space frame actually looks like. And then diagrid is a framework again, and diagonally intersecting metal, concretes or wooden beams that are used in the construction of buildings and roofs. So coming back here, sorry, yeah, coming back here, this is how this building looks like. So it's definitely not a folded plate structure. It is not a space frame because no truss is here. It is not a diagrid structure because diagrids have diagonal grid in it, and the other option is pneumatic structure, and it is very easily clearly visible that it is a pneumatic structure. It is being held by with the help of compressed air. So our answer would be pneumatic structure. Moving forward, question number 13. The following image is a shell structure having the form of paraboloid, hyperbolic paraboloid, cylindric and conic. Uh, we would learn what all these four shell structure shapes are. Then we will answer this question. So a paraboloid is a quadric surface that has exactly one axis of symmetry and no center of symmetry. The term paraboloid is derived from parabola, which refers to a conic section that has similar property of symmetry. So what happens in a paraboloid is that there is one axis of symmetry, and then it looks like a bowl kind of thing, a paraboloid basically. It comes from a parabola. Hyperbolic paraboloid is a saddle surface, and we have talked about hyperbolic paraboloid before, and it is a ruled surface. It is not developable. Cylindric. A cylinder is a three-dimensional shape consisting of two parallel circular bases joined by a curved surface. Then conic. Conic or a quadratic curve is a curve obtained from a cone's surface intersecting a plane. So this is how all these four shapes look like. So if you go back to the image, you can see it's not a parabola, it's not a cylinder because there is a curvature, it's not a cone because we all know how a cone looks like. It's a hyperbolic paraboloid. The image I have added here, you can see it's this one curve and this one curve. There are two curves. But when you use it to form a whole circular thing, so there is this one curve happening and there is this one curve also happening. So it's a hyperbolic paraboloid. There are two curvatures involved. Moving forward, question number 14. Following illustration is example of what kind of curvature? I think this was our second question, and we discussed all these terms. We will just quickly go to these three terms again and answer this question. So monoclastic surfaces have single curvature shell. They are curved in one direction and come in the form of barrel bores or conoid shells. They have one curve only and one axis along which the curve moves. Then synclastic, these shells are doubly curved and have similar curvature in each direction. Synclastic surfaces are those in which the centers of curvature are on the same side of the surface. A dome is a good example of a synclastic shell. It is doubly curved and can be formed by rotating a curved line around an axis. Anticlastic surfaces are those in which the centers of curvatures are located on opposing sides of the surfaces. Just what we talked about hyperboloid, paraboloid. They are doubly curved, but each of the two curves are opposite direction to the other. Examples are saddle points. Hyperbolic paraboloid and hyperboloids are considered anticlastic shells because they are saddle shaped with different curvature in each direction, and straight lines can be drawn off the surface. Then we saw these images, and going back, it is very evident that it has two curvatures, so it is not monoclastic, and the center of both the curvature is in different directions. That means it is not synclastic, it is anticlastic. And bipolar is not a curvature type, so not covering it. Moving forward, question number 15. Folded plate structural system can be used for roof, wall, staircase. We all know what a folded plate is. I will not go again in this detail. So the applications of folded plate structures actually include roof structures, wall structures, floor structures, and staircases. All these four examples are shown here, how it looks like, how it is being used in the roof of that seating. We can see how it is being used as the wall in that structure. We can see how it is being used in a floor, that is also we can see, and how it is being used as a staircase. So staircase is what? It's just a folded plate with a riser and a tread. It's folding plate, so yeah, it's being used as a staircase also. So our answer would be all of the above. The structural system used in Yokohama International Port Terminal is membrane, folded plate, grid, or pneumatic. So this is how the Yokohama International Port Terminal look like. It is at the Osanbashi Pier. It is the main international passenger pier at the port of Yokohama, located in Naka Ward, Yokohama, Japan. Osanbashi is the oldest pier in Yokohama, originally constructed between 1889 and 1896. But this structure has been made in 2002. The architects were Alejandro Zairapolo, Farshid Musavi. The main contractor was Shimizu Corporation, Towa Construction Corporation. The height of the structure is 15 meters and the floor space is 34,732 meters square. This is another internal image of the Yokohama International Port Terminal. And then we were asked if it's a membrane structure, it's a folded plate structure, it's a grid structure, it's a pneumatic structure. So it's definitely not a grid structure, it is not a pneumatic structure, we all know it's not a membrane structure, and it is very evident that it's a folded plate structure because you can see folded plates in all its form. Internally, externally, everywhere you can see the folded plates. So our answer would be folded plate. Question number 17. The following illustration is a king post truss, queen post truss, Harvey truss, or Baltimore truss. So this is the image that has been given. And yeah, so we covered Baltimore and Harvey truss. We will just talk about king post truss and queen post truss here. So a king post is basically a central vertical post used in architectural or bridge designs, working in tension to support the beam below from a truss apex above. So if there is a truss in which the central post is being used, which is called a king post, it is a king post truss. A queen post truss. A queen post is a tension member in a truss that can span longer openings than a king post truss. And a king post truss uses one central supporting post, and in a queen post truss there are two supporting posts at different points. As you can see from the image, this is how a king post truss looks like. There is one central post that is holding the truss together, and in queen post truss there are two vertical members that are holding the truss together, attaching at a point in the rafter. Baltimore truss, just a quick revision. The Baltimore truss is a subclass of Pratt truss. We all saw what a Pratt truss was, and the Baltimore truss has additional bracing in the lower section of the truss to prevent buckling in the compression members. So as you can see what a Pratt truss looks like, and then Baltimore truss is a type of Pratt truss, but it has more bracings and more lower bracings to support the lower section of it. It is mainly used for rail bridges and showing off a simple and very strong design, and it has more bracing to avoid buckling in the compression members. Then we come to Harvey truss. Harvey trusses are essentially the opposite of Pratt trusses in terms of geometry. In fact, looking at a Pratt truss upside down will visualize a Harvey truss, The entire structure is still relatively the same, but the diagonal braces are now occupying the opposite side of the unoccupied joints. And the switching in position of the diagonal members as compared to Pratt truss has a very important effect structurally. So we look at all these images, how a king post looks like, how a queen post truss looks like, how a Baltimore truss looks like, how a Harvey truss looks like, and the Pratt truss looks like. So the answer is Harvey truss. Although I have a feeling that this is a Pratt truss, not a Harvey truss, but that is not given in the option, and it is definitely not just a king truss, and it is not a queen truss, and it is not a Baltimore truss also. So it looks like that it is an example of a Pratt truss, but however the closest answer is Harvey truss. We'll go with Harvey truss. Pneumatic structure is used in inflatable tea house Kengo Puma, Fuji Pavilion Expo 70, both A and B, and none of the above. So to be able, we all know what a pneumatic structure is by now. We have covered in almost all the questions, and you must have seen all the lectures also. So you know, you all are pretty well aware of what a pneumatic structure is. I will not talk about it again. I will just show the two examples that have been given, and then we will answer this question. So inflatable tea house Kengo Puma and Fuji Pavilion Expo 70. So this is how the inflatable tea house Kengo Puma looks like, and this is how the Fuji Pavilion at Expo 70 looks like. So it's very evident that both of these structures are pneumatic structures. So our answer would be both A and B. So again, as I have mentioned before, to be able to answer these kind of questions, you have to remember how the building looks like. Otherwise, you won't be able to answer these kind of questions. So this is all for today. I have done 18 questions for today. Now we will move forward with question and answer round. Then for the of the live session, you can ask your questions and doubts, and I will try to answer the questions as per my capacity and knowledge. And if I do not know the answers, I would explain it in the next live session. So please join in the next live session. So whatever your question is, if you have any kind of question, please put it in the chat box. I will read it and I will try to answer your question. And in case there is no question, in 15 minutes we will end the session. So you have no question, Rajat? Okay, thank you. Thank you for appreciating. So I would just still wait for 10 minutes in case anyone joins and want to ask anything. If you wish to leave, you can leave. So we have waited for 15 minutes and no one has joined and no one has asked questions in this time. So I would conclude today's session, and for everyone who would be watching this later, if you have doubts, any doubts regarding the week 6 assignment 6, please let me know in the next session. I will try to answer it. Thank you everyone. Thank you so much.